Morning everyone, my name is Ram Ganesh and I'm here to present my project on the hardware implementation of LeNet 5 convolutional neural network for MNIST digit recognition. LeNet 5 introduced by Jan LeCun in 1998 is one of the foundational CNN architectures designed specifically for handwritten digital classification. It's simple yet effective architecture inspired many modern deep learning models. The primary focus of my project was to implement the forward interference path of the LeNet 5 entirely in hardware using HCL tools like Xilinx, Vivado, and VT's HLS. My objective was to create a resource efficient design capable of high accuracy while ensuring real time performance, particularly for embedded and resource constrained applications. This includes the software frameworks like TensorFlow or PyTorch. So coming to the so to the introduction of my Linux. What's it about the introduction? Let me give you the brief overview of the Linux 5 architecture which I implemented. So it starts with an input layer that processes 32 cross 32 grayscale images. These are the standard dimensions for the MNIST datasets, which contains handwritten digits from 0 to 9. This architecture includes convolutional layers that extract features from the input images by applying 5 cross 5 filters. These layers detect patterns like edges, textures, and shapes, which are crucial for understanding the structure of each digit. Following the convolution, there are pooling layers that reduce the size of the feature maps. This process lowers the computational complexity while making the model robust through slight variation in the input. And finally, the network transitions to the fully connected layers where all the extracted features are aggregated and mapped to output probabilities for classifications. The ReLU activation function is applied for the convolutional and fully connected layers to introduce the nonlinearity. This nonlinearity enables the network to learn and represent complex patterns in the data, which would not be possible with just linear transformations. So, yeah. This is the comparison between the LeNet 5 and the AlexNet. So yeah, the LeNet 5 is nothing but like it gets the output of the 10 output units, but whereas the AlexNet gets the output of the 10,000 output units. And coming to the methodology, for my hardware implementation, I followed a structured and systematic approach. First, I broke down the architecture into individual components, as you can see here, the conventional layers, pooling layers, and fully connected layers, and implemented each one using the Verilog and VHDL. This modular approach ensured that I could test and validate each part independently before integrating them to the complete design. To optimize the resource usage, I used the 16-bit of precision FP arithmetic. This choice reduced the overall resource requirements, such as the LUTs, BRAM blocks, without compromising the accuracy of the model. I also incorporated the pipelining and parallelism into the design. The pipelining allowed me to split the computation into stages, enabling to multiple operations to be performed simultaneously. Yeah, and coming to the simulation and validation, I used the Xilinx Vivado and VT's HLS. These tools allowed me to visualize waveforms and verify that the hardware behaved as expected. I tested the implementation using the MNIST dataset, which provided a robust benchmark for handwritten digit recognition. And yeah, these are my 3 steps, like you can see: layer implementation, testing and validation, performance analysis. Yeah, and coming to the testing and evaluation, the testing was a crucial part of my project. I generated the test cases from the MNIST dataset and used these to verify the functionality of each layer. For example, I validated the convolutional layers by ensuring that they correctly applied filters to the input images and produced that accurate feature maps. Similarly, I tested the pooling layers to confirm that they reduced the feature map size without losing important information. Simulation tools like Xilinx Vivado and visualization tools like GTK Wave were really helpful in this process. They allowed me to examine the data flow and ensure that all layers were working correctly together. I also evaluated the implementation uh, using several key metrics. This includes like resources utilization such as LUTs, DSP slices, and BRAM blocks. And finally, I accessed the accuracy of the model to ensure that the hardware implementation matched the performance of its software counterpart. So yeah, the, coming to the results from my project, uh, the hardware implementation achieved the 96.02%, a remarkable improvement, which is comparable to the software-based implementation of Linet 5. This high accuracy demonstrates that the use of 16-bit of precision arithmetic did not compromise the model's ability to classify digits very effectively. From a performance perspective, the optimized pipeline design allowed the implementation to achieve a maximum clock frequency of 200 megahertz. This high frequency contributed to reduced inference latency, making the design suitable for real-time applications. In terms of resource utilization, the design effectively used the FPGA resources, including the LUTs, BRAM blocks, and DSP slices. So overall, these results validated my approach and showing that it is possible to implement a high performance CNN like Linet 5 entirely in hardware, even in resource constrained environments. So you can see the generalization, like this model appears to generalize well to the unknown data based on the near alignment of, because as we discussed further, it is also can do the nonlinearity. Coming to the convergence, both measures plateau by approach 10, indicating that the model parameters have been optimized. So to conclude the my project, this I successfully implemented the forward path of Linet 5 for handwritten digit recognition using HTL tools. They are designed achieved a balance between high accuracy and hardware efficiency, making it a strong candidate for the embedded applications. Uh, Coming to the future directions, I want to string the implementation of the training to support the training with the back propagation, which would allow me or the model to adapt to the new datasets directly in hardware. Additionally, I aim to deploy this design on the real-time devices, showcasing that this particular practical utility in the scenarios like IoT and mobile applications. And finally, I want to explore the scaling the architectures to handle more complex models like RSNet and larger datasets, further pushing the boundaries of hardware accelerated deep learning. Thank you. Thank you for your attention. Yeah. I hope this presentation has provided insight into the potential of hardware accelerated CNS. Yeah. Any questions?